So we're going to deal with determinants. And a lot of times determinants are just presented as a formula, but what the context is, given a square matrix M, and you can have sort of different sizes, like it could be an n by, it's a square matrix, so it's n by n. It's like a map that you associate with a number. And the idea is, what you want to detect with this number somehow is whether you want to detect whether M is singular or not. Remember, if it's singular, that means it has no inverse. Or over here, if it's not singular, then it does have an inverse. And if you use this as a matrix of coefficients of a linear system, then a homogeneous linear system based on M, if it's singular, has a free variable, right? And so an infinite number of solutions. On the other hand, if it is non-singular, then the homogeneous linear system has all variables leading. So the idea here is to have this sort of, say, take in the matrix M and find some number that detects whether or not a linear system based on this matrix has one solution or an infinite number of solutions. If it's homogeneous, it always has one solution, so it's consistent. So these are the only two possibilities, either infinite number or one solution. Like all variables are leading, or at least one free variable. And correspondingly, if it's non-singular, it'll have an inverse, and if it's singular, it'll have no inverse. Okay, so the idea then is that there's two sort of observations. One is that row operations do not change the number of solutions. Row operations cannot change this number. What we're going to, in the end, we're going to call this map the determinant, or the number that's produced the value of the determinant. So this sort of like has two meanings. One is it's the number that results the target, the image of this map, or you can just think there's the map itself. Okay, so the row operations can't change this number. So it has to work nicely with row operations. And two, we can look at small n examples to get a clue about how this stuff might work. So the idea, the strategy is, and the strategy the text takes is, we want to look at some principles. And it turns out that if we define simple principles about how this works, it completely defines the map. And it turns out there's only one map that actually does this. So there's actually a unique situation here that it's not like there's like a whole bunch of maps and we're just going to select one that detects singularity. There's really only one map. And one of the ways to do it is to just see how it operates under row operations, and we need some extra clues from example n equals 2, okay? And the third one is, all this has a geometric interpretation. That is, the determinant, the value of the determinant is going to be the area or volume of some entity. If you think of the vectors as embedded as in a Euclidean space, like arrows, then they sort of define an area or a volume, and the determinant gives you the area or volume corresponding to certain vectors. Okay, well, it turns out then, so the matrix sort of, from the matrix, you can get a particular volume in space, and then what's going to happen is the determinant, that volume is going to tell us, or area, if it's two-dimensional, is going to be the value of the determinant, and so there's going to be a geometric interpretation. So what we'll start with here is number 2. Let's look at a simple homogeneous linear system. Okay, of 2 equations and 2 variables, and say, so the idea here is that we want to be able to detect, the key thing is going to be the free variable thing, because if we're looking of a linear system, so our matrix M here is going to be A, B, C, and D. But we're thinking of it as the matrix of coefficients of the homogeneous linear system, and then we want to apply this thing with variables. So what we want to do is, we want to bring this to echelon form. Now, there's lots of cases where, for example, C is 0 or A is 0, or different cases like that. So let's, for simplicity, we can suppose it's going to turn out that the case with all of them non-zero will contain all the other cases. So we don't have to, so this is the informative case is going to be that, or the one that we're going to look at, are not 0. We can go through and look at the other cases, but that's not the issue, because let's say they're not 0. Then we can do the row operation here, minus C over A times row 1 plus row 2. Now, you can see that this one assumes that A is not 0, right? If A is not 0, then this is equivalent to X being leading, right? Because if A is not 0 and C is 0, then X is leading. If C is not 0, then we can get rid of it by this means, well, we can't get rid of both of them. We can't get rid of both A and C. We can only get rid of one of them. So if A is not 0, then X is going to be leading, okay? So let's do this row operation here. Well, it doesn't affect the first one, but it does, but minus C over A, well, the A cancels it. This produces minus CX, so this will be 0 here. And then here, this will be dy plus, well, actually it'll be plus, but it's because then it'll be minus C over A times B. So it's minus C over A times Vy equals 0, okay? Because I've just taken minus C over A times Vy and added it to row 2. Then, if I do, to simplify things, I do A times row 2. This becomes AX plus Vy equals 0. And then I can factor out the Y here. This is going to be, but if I multiply through by A, that'll introduce an A here and cancel off an A here. So I'll have AD minus BC times Y equals 0. Okay? So the idea then is that, well, this is an echelon form. And if it's going to be, so we can see, since A is not 0, X is leading, right? So this number here controls whether the system is singular or not. If AD minus BC is not equal to 0, then Y is leading, and this is non-singular. Do you see that? If AD minus BC is not zero, then Y is going to be leading. It'll have the value zero, so the solution will be, but Y will be leading in its row. Okay? On the other hand, and then there'll be one solution, which is 0, 0. On the other hand, if AD minus BC equals 0, then Y can be anything, and Y is free. You have an infinite number of solutions, and the system is singular. So this is a candidate sort of map. A B, C, D to AD minus BC. And we've sort of seen that it does the right thing in terms of, and you can see also that we know from this connection that this matrix is not going to have an inverse. Okay, so now, since we have an example of, you could go through and do the same thing with a 3 by 3 matrix and you get a more complicated formula. But then let's say that we wanted to know, we could then examine the row operations with respect to this quantity. And here's the results. I mean, we could go through and do that, but I think it's not important to see the algebra as much as one. If I do K row 1 plus row 2, or K row 2 plus row 1 for any K, AD minus BC does not change. Okay, so this if we want to call this a determinant, it doesn't change if I do a row operation here. Now we'd have to go through and see it. That's an interesting result, and it's going to turn out that. So what we're going to sort of see is that this is going to give you an inspiration for a property of the of how determinants work. Now, what about the other row operations? Well, if we do row 1, row 2, well, what happens up here is that you can sort of see that C becomes A, and A becomes C, and D becomes B, and B becomes D. And you can see this is the same thing as AD minus, this is CB minus AD. This equals minus AD minus BC. So if I interchange the two rows, AD minus BC changes sign. Well, changing of the sign doesn't change. In other words, it doesn't change as 0 non-zero. So 0 and minus 0 are the same. So if something's singular, it stays singular, and if it's not 0, like if it's 5, then you switch the sign, it's minus 5. So that's still not. You're still going to have all variables leading. So this is okay. This doesn't change. It doesn't matter, but we're going to want to say that somehow this thing will change the sign of the determinant. And the third one is, what if I do K row 1? Well, if I do K row 1, then how's that going to change here? Well, if I look at the K here, that's going to change because A is going to have an extra K here. That's going to change this number to KAD minus KBC, which equals K times AD minus BC. So this row operation, now if as long as this has to, K is not 0, and that's one of the restrictions, we can't just multiply a row by 0 because that changes the linear system. So if this is not 0, this just rescales this number, makes it bigger. So, and that also works with singular versus non-singular. So what we assume then is, well, this is true of all the maps. So we have the determinant of M of, say, row 1, row 2, because we're going to assume that the determinant of the matrix is a function. Let me see, let me just call it, what other notation do I want to have? Okay, let's see. Let me just make sure I'm going to do the same. I'm not going to do something weird. Okay. It goes through, and I actually, these are all, the first of the chapter goes through this in more detail with both 2- and 3-dimensional matrices and shows that the same thing happens here for the analogous number for a 3x3 matrix. And let's see. Okay, so here is, okay, yes, here's the, so that just here. Okay, so if we have some determinant for a fixed matrix M of n by n, then we have a determinant. So this is going to be 2x2. The determinant is a function of, it's going to be sort of depend on the rows only. So we can think of it as depending on the rows. So if I do what's going to happen is, if I then, this is going to equal the determinant of row 1 times k plus k times row 1 plus row 2. So yeah, I've done the row operation, and the situation is that if I change the row here, this number doesn't change. That's our first property that we're going to assume. The second one is the determinant of row 1, row 2 equals minus the determinant of row 2, row 1. 3 is going to be the determinant of, say, k, row 1, row 2 is going to equal k times the determinant of row 1, row 2. This is different than multiplying a matrix by k, right? If I multiplied 1, 2, 3, 4 by 5, that would equal 5, 10, 15, 20. It would multiply both rows, right? So this operation is not doesn't correspond to multiplying the matrix. It corresponds to the row operation where I've expanded. Now I've started here with row 1, row 2, but so this third one I could also write as the determinant of row 1, row 2 equals 1 over k, determinant k, row 1, row 2. But that's confusing. It's sort of like, the idea here is this is a simpler way of thinking about it. So you can sort of think about this as, this is the transform side. This thing is going to equal minus this one. This one is going to equal the same as this one. Okay, so now that is what's here. That's what's given here with these properties. Now, we also have sort of a normalization issue that what we're going to do is we're going to sort of have the determinant of the identity matrix equaling 1. Okay? So that's just a normalization, saying, well, this is non-singular, and we're going to say, well, this could be any non-zero number, because since it has to be non-singular, but we're just going to this sort of acts as a normalization that the determinant of the identity matrix, and there's really maps for every size. Like we could go so that the determinant of the 2 by 2, the 3 by 3, they're all 1. So we're thinking of sort of one sort of map for each size. Now, let's see what these properties lead to when we apply them to certain matrices. For example, let's see what the determinant of A0, 0B is. Okay, well, we can do is we can say, well, this is equal to A times 1, so I can pull out the A. That's equal to A times the determinant of 1, 0, 0B, which equals, and I can pull out the one from row B, so that's going to be AB times the determinant of 1, 0, 0, 1. And since this is the determinant of identity, this is equal to A times B. Okay? So you can see how this really works for any size matrix. So the determinant is equal, if the matrix is diagonal, if it only has diagonal entries, it's going to be the product of those diagonal entries, right? So you can see then, if any one of these entries is 0, this is essentially just like we put the matrix into reduced or echelon form, but we hadn't normalized it, and then we'd see, okay, well, if any one of these is 0, this is going to be a free variable, and it's going to be singular. So we can see that if either A or B is 0, the matrix will be singular. Now, then what's going to happen is that we can see that if, and you can see here that this AB portion here is the A is, well, let me call this D to match up with what we did before. Okay, well, this piece here is the part of this formula where B and C are 0. So this part of the formula, this first one here, is just given by that. Now let's see what happens if we have the determinant of A, B, C, D. And let's suppose that under the condition that, say, A is not equal to 0. Okay? Well, if A is not 0, then I can do the row operation. So this is sort of, the row operation corresponds to minus C over A row 1 plus row 2. Under this row operation, this determinant doesn't change value. So this is the same as the determinant of A, B, 0, D minus C over A, B. Because we've just used the property that a row combination operation doesn't change the determinant. Okay, well, here, then we can let's see, how can we, what we want to do is sort of see that we can simplify it a little bit by multiplying, say we do A row 2. If we do that, then what's going to happen is that we can't just, well, let me see how to say this. We do the row operation A times row 2. What's going to happen is that's going to multiply this by A, right? Then the point is that I can factor that out. So this is going to equal, let me see, let's do, this is the determinant. It's not going to equal, how do you say? Oh, no, let me do it, say it this way. It's sort of used thinking of it this form here, right? No, let's look at this form here. What I want to do is, I can see how to do this. What I want to do is I want to write this as the determinant of A, B, 0. And what I'm going to do is I'm going to factor out 1 over A times AD minus BC. I want to factor out a 1 over A, so I have to put in this first term in A times 1 over A, which is 1, so I can pull out the 1 over A, because then I can see that this 1 over A multiplies formally the 0 here, so it multiplies the whole row. And then if I have K times a row, I can pull that out. So this is going to equal 1 over A times the determinant of A, B, 0, AD minus BC. Okay, so then I have to say, well, I can do a row operation. If this is let's see, how can I say this? What I'm trying to do is show that these properties lead to this formula, right? And the idea is then that if I can get rid of this B, then I have a diagonal matrix, and it's going to be, it will just be the product of the diagonal entries. So that's my goal. That's what I'm trying to do here. And the idea then is I can think up some row operation where if this is not 0 right here, right? Then if this is not 0, then I can sort of do B times 1 over that and add it to this, and that will make it 0. So if A, B minus BC is not equal to 0, then I can do 1 over AD minus BC times B times row 2 plus row 1, and that's going to produce 1 over A determinant of A, 0, 0, AB minus AD minus BC, okay? In which case, I can say this is 1 over A times the product, because now the matrix is diagonal, times A times AD minus BC. The 1 over A's cancel, and you have AD minus BC. The point is, you can get the point is, now if this is 0, then some things happen that implies some constraints on this, and you can get the same formula. So if AD is 0, then either one of these is 0. Well, if it is 0, then you can see that this matrix is singular. Okay, and you're going to end up then with the singular being corresponding to this being 0. So it's a little bit hard to say. The idea then is that these principles lead to this formula. Okay, so that's just the point here. Now, the question, this whole scheme then leads to, you don't need the formula. What you can do is to find the determinant. You can, because basically those principles completely determine what is a determinant, and you can prove that it's unique, and it's the only one, and it works. So if we want to find a determinant, all we have to do is apply those row operations. So let's say that we want to find the determinant of the matrix, say 1, 2, 4, 3, 6, 8, and say 9, 4, 10. I have no idea what, okay? So what do? Well, I say, I think I can do row operations to find the determinant by doing row operations on the matrix here. So this is going to be equal to the determinant of, well, I'm thinking of the row operation, minus 3 row 1 plus row 2. which will give me 0, minus 0, and my 3/4 is 12. This will be minus 4. And then down here, this will be, well, that's with row 2. Then I can do minus, that's not quite what I intended, minus 9, row 1 plus row 3 will give me 0, and minus 18 plus 4 is minus 14, and minus 3/4 is 12, is minus 2, okay? So these determinants are equal, because I did row combination operations. Then I can see that this is the determinant of, well, I can sort of flip the interchange rows here. This is going to equal minus the determinant of 1, 2, 4, 0, minus 14, minus 2, 0, 0, minus 4. Okay? Now, one of the things I can see right away is, this is an echelon form. Now, I can do a row operation to get this one to cancel this number and this number. Once that's done, I can use a row combination operation to use this entry to get rid of that one. So this is going to equal the determinant of 1, 0, 0, 0, minus 14, 0, 0, minus 4. And that's going to equal minus 1, the product of the diagonal entries, minus 14 times minus 4 times the determinant of 1, 0, 0, the identity matrix. So so these are 3 signs, so it's going to be minus 14 times 4, which equals minus 56, 40 plus 16. So you can do, now it turns out that this method of finding the determinant is faster computationally than any other method. So now for 2x2 matrices, the formula is going to be faster because you just plug in the numbers and calculate it. For the 3x3 one, it could sort of, the formula is, and we'll run the formula, is a little bit tedious, but it probably is about the same speed. But for a 4x4 matrix, you definitely want to use the Gauss's method. And if you put it on a computer, that's the way to go. So you can use Gauss's method to find determinants. And that's basically the game. That's basically what we want to be able to do is most of the chapter is taken up with proving that these principles do determine the map, and the map is unique. So most of the chapter is a big proof, and we're sort of going to ignore that. So what we want to do is practice. I flipped. Let's see. How did I get the negative? I interchanged 2 rows. Row 2 interchange row 3. See, because I flipped. Oh, put it on the wrong one. I flipped. Oh, there. Row 2. See, I flipped these row 2 and row 2 and row 3. I flipped them and it introduced a sign. So if you interchange, okay. So let me